Okay, we're going to continue our discussion of the modulus function with the thing that annoys everyone the most, drawing graphs with it. Drawing graphs is probably the most complained about thing in maths, at least in my experience, with me as well. Can't stand it. But unfortunately, it's very, very useful. No matter what the function is, if it's just a standard quadratic or a cubic or a trig function, a sine, a cos, or a modulus, it is unfortunately very, very useful to sketch a graph. Couple of reasons for this. First one is it allows us to see what is happening with the function at a given point. What is happening to x as y changes? What is happening to the function as x changes? What is happening at x equals 0? What are the intersection points, etc., etc., etc. And these are all very useful things in real life when we're trying to do these calculations. So let's start with then, how would we go about drawing a graph that looks like this? So it's just a standard y equals x graph with my modulus function applied. Now, there's a couple of steps that we want to go through whenever we're drawing one of these graphs. And no matter how complicated the graph is, we always want to keep going through these steps. And it may seem quite long and arduous, but it will get us the right answer 100% of the time, as long as we don't try and skip them. Right, the first thing we want to do is we want to break up our function. Now, what I mean by that is, have a look at our function. In this case, I've written it with a y, but of course, f of x equals the modulus of x is probably going to be more common, and that's the one I'm probably going to be using from here on out. But let's stick with the y for now. We want to break it up. And the way I like to say to break it up is as follows. Start off with y equals x. Most graphs are going to boil down to y equals x with a load of rubbish, with a load of gunk stuck to it. Maybe there's a 2, maybe there's a +7, maybe there's a cos or a sine or a tan, or maybe there's a modulus. But at the core, all of our functions are just a something y equals something x. So start off with that. So if I plot this on I get a coordinate axes going, I'm going to start off by just plotting my equation without any gunk, usually y equals x. So hopefully we all know that is just going to be a straight line through the origin. Then, and you may want to do this on multiple different graphs, you may want to sketch it out a few times, as long as and annoying as it sounds, best to just get the marks and move on and do a couple of rough sketches along the way. So what I'm going to do is I'm going to start adding my gunk back in. I'm going to stop calling it gunk now, actually. But I'm going to start adding stuff back in. So in this case, the only thing I've got to add back in is my modulus function. So I'm going from y equals x, it's an arrow, not a greater than. I'm now going to y equals the modulus of x. So let's have a look. What is actually happening in this function? Well, I am taking all of my x coordinates and I am applying the modulus. What does that mean? I am forcing them to be positive. If I'm forcing them to be positive, well, I can have a look at my y equals x graph and see what happens. If I take my x coordinates here, anywhere along here, and I find the associated y value on my graph, well, hopefully we can all see that these are going to be positive, which is what I want. I want everything to be positive. On the left-hand side, though, any of these x values, if I draw lines down to my graph, I notice that they are now negative. I am now on a negative y value. Couple of points first. Very, very common trick, or very, very common misconception rather, is that this means the x coordinate has to be positive. But when we're looking at it in terms of a graph, it means that whatever happens to the x, whatever happens, the function applied to it must be positive. So it's not that we can only be on the right-hand side of my graph, it's that we can only have associated positive y coordinates with my x, as I've shown here. Every point over here, I go up to a positive. Every point here, I go down to a negative. Well, how do I solve that? Well, if all of my points here are negative, then I can just turn them positive, right? Yeah, that's it. I can just turn them positive. These are all negative. So I'm going to flip the graph. I'm going to invert it. I'm going to stick a mirror along this line like we did in primary school. And I'm going to reflect it into the positive area up here. Now, a couple of points. It does need to be a perfect reflection. Any of you wanting to know more details, that means these angles are going to have to be the same and some other angles are going to have to be the same, but we won't worry about that. But it does mean that it needs to be a perfect reflection. And I will just sketch our final answer then, which will be a graph that looks like this. And this is my y is equal to the modulus of x graph. Okay, now let's have a look at a more complicated example where we have a lot more gunk. Yeah, a lot more stuff stuck to my x. And I have 4 very poorly drawn coordinate axes here. They're not very pretty, but what I want this to get into the habit of doing is drawing out, or at least roughly sketching, each stage in the process. So, step 1 is we are going to break up this function into its bare essentials. What is actually happening in this function? Well, I've got a y on one side, which is good. I don't have to worry about that. And then I've got an x that's being multiplied by a 2, adding 1, and the whole thing's being modulus. So, how can I break this up? Well, if you remember what I said earlier, the very, very first thing that we want to break it down into is a y equals x graph. 99% of the time, it boils down into being a y equals x graph with stuff happening, with transformations occurring. And this doesn't just apply to the modulus, it applies to any transformations that you'll do. So, I'm going to start off with y equals x. And I'm just going to sketch that graph. Now, maybe as you get more confident, you can start skipping this step. But to start with, just do every single step. You can't go wrong. Now we want to find out what is happening to my x. Well, we've got 3 things. So my x is being times by 2, it's having a 1 added onto it, and then it's being modulus. And it's important that I remember the order. If I get the order of this wrong, then my graph will end up looking wrong. So maybe go back to bid maths or kind of just intuition. What is happening to my x first? Well, first and foremost, it's being multiplied by 2. So that's the first thing that we're going to do. That's the first transformation. Y equals 2x. Now, I'm not going to go into detail about these transformations here. I'll save that for a later chapter. But let's sort this. Y equals 2x. Well, that is just going to be a y equals x graph with a steeper gradient. A 2 times steeper gradient, to be exact. Yeah, that's steep enough, I think. Y equals 2x. What's the next thing that happens? Well, we add a 1. If you need to write out the order, no shame in it at all. These working things, don't worry about how silly they make you look. If you have to write 2 plus 2 out, just do it. We're adding a 1. Y equals 2x plus 1. Again, I won't go into the details of the transformation, but hopefully we remember that we are outside of the kind of x system, so we are applying this plus 1 to the y coordinates. We are pulling my graph up by 1, so I'm pulling this graph up by 1, and it will look like that. It's also never a bad idea to keep track of our intersection points. Never a bad idea. That's a very common question. Where does it intersect the x-axis, etc., etc., etc. And then for part 4, our 4th graph, what is the last thing happening to this function? It is being modulus. Modulated? No, modulus. We'll go with modulus. It's being modulus. That's not a word. Y equals the modulus of 2x plus 1. Well, we saw in the last example, in order to modulus a graph like this, everything positive can stay and everything negative must be mirrored. So we're still going to be intersecting at 0, 1. This point here is still going to be the same as this point here, but we have to reflect it in my x-axis to ensure I do not go negative. Again, don't fall into the trap of thinking, well, I'm crossing the y-axis, my x-coordinate's going negative. That's not the concern here. The concern is when the x-coordinate is negative, is my graph negative? And here we have prevented that.